Hello and welcome back to this video series regarding the Intermediate Math League of Eastern Massachusetts. Today we're going to be finishing up the number theory section for Meet 5. So let's get right into it. All right, so first we're going to talk about simplifying set theory calculations. And today's video is going to be focusing all on set theory stuff. And so that's talking about sets and unions and intersections especially. If you don't know what those are, I very highly recommend that you watch the first video that I published in Number Theory Meet 5, because that's where I start talking about sets and unions and intersections. And today's video is just building on what we learned last time. So if you don't know what unions and intersections and sets are, I very highly recommend you watch that video. Otherwise, I implore you to keep watching. So when it comes to set theory calculations with unions and intersections, sometimes you can change around the order that you do things or simplify them with a few certain rules. So the first rule is talking about unions. If you have more than two sets that you're finding the union of, so say it's not just A union B, but say it's A union B union C, right? It doesn't matter what order you do those unions in. So this is what the rule is explaining here with what I have written down. Say you were given this in a question, A union B union C, but A union B is in parentheses. You could change it around to be A union B union C, or B union C is in parentheses, because the order that you do the unions in doesn't matter, as long as you do all of them by the end. And just as a quick reminder, union means all of the numbers in all of the sets. So if my set A were the numbers 1 and 2, and my set B were the numbers 2 and 3, then A union B would create a new set of 1, 2, 3. All of the numbers in all of these sets. And just as a reminder, if you're finding the union of two sets and say one number, so in case it's 2, is in both of the sets, then you don't repeat that number in your union set. You only include it once. All right, so next, the same rule applies to intersections. So if you were to find A intersection B intersection C, right, say a question gave this to you and had one of the intersections in parentheses. You can just remove that parentheses. It doesn't matter what order you do the intersections in either. So I could start with B intersection C first and then find the intersection with set A. And I'm still going to end up with the same answer. And just as a quick reminder, intersection means the numbers that the sets have in common. So say my set A, I'll use the same example. My set A is 1 and 2, and my set B is 2 and 3. Then the intersection of these two sets would be just the number 2, because 2 is the only number that is included in both of them. So 2 would be my intersection set of A and B. And the final rule, and this is just one that you're going to have to memorize, is if you have A union B, so I'm actually looking at this side, by the way. If you have A union B, in parentheses, intersection C, you can't change around the order, right? So you can't do B intersection C first or A intersection C first. That doesn't actually work because you're talking about two different operations. Just in the same way that if you're doing multiplication and you're doing 3 times 5 times 9, right? You could switch around the order. You could do 5 times 9 times 3 or 3 times 5 and then times 9. And you can do the same thing for addition. You can switch around the order. But it's kind of like that, where if you have 3 times 5 plus 9, like this, you have to do the 3 times 5 first. You can't do 5 plus 9 first, and then times 3 because you get the wrong answer. The same things apply to unions and intersections. So you can only switch around the order when they're all the same, so they're all unions or all intersections. But if you have something like this, where it's A union B, and then intersection with another set, C, you can't just switch around the order. However, there is one thing that you can do if you have this case. And that's that you can change it to this, where instead of finding the union of A and B first, you find the intersection of those sets with C first, right? So you find the intersection of A and C, and you find the intersection of B and C. So you find those intersections individually, and then you find the union of both of those intersection sets. And this is a rule that you're just going to have to memorize. It's not going to show up very often, but it might. So I thought it just might be handy to have in your back pocket. All right, so next we're going to talk about the inclusion-exclusion principle. And this is a principle that when it comes to finding the union of two sets, the amount of numbers in that union of two sets, you can kind of simplify that math a little bit so you don't have to just do it by brute force. But there's actually a formula that you can use to find it. So when you're finding the union of 2 or 3 sets, so say you need to find the amount of numbers in A union B, or the amount of numbers in A union B union C, these are the 2 formulas that you can use in order to find the amount of numbers. Now, this first one is kind of simple, kind of only has 4 terms, and I'll explain what those mean. The second one is really overwhelming. It has a lot of terms in it and can be a lot to comprehend. So I'm going to just get rid of this second equation for a bit and just explain what the first one means. And then after I finish, I'll return back to the second one because you'll see that they're actually really similar. All right, so say you need to find the amount of numbers in A union B. And that's what these symbols mean. They kind of look like absolute value symbols. These mean the amount of numbers in a certain set. So if I had this means the amount of numbers in set A. This here means the amount of numbers in the set of A union B. So say we needed to find that. Well, what we can do is we can find the amount of numbers in set A and the amount of numbers in set B and add those 2 together. And then from that, subtract the amount of numbers in A intersection of B. So what that would look like, and I'll use a really simple example to explain it, is say my set A had the numbers 1, 2, and 3, right? So here's my set A, pretty simple. My set B has the numbers 3, 4, and 5. Now, if we needed to find the amount of numbers in the set of A union B, well, these sets are really small, so that's pretty simple, right? I can just do 1, 2, 3, 4, 5, and just find the union set and write it out, and then realize that there are going to be 5 numbers in this set, and I've solved the question. But the reason that we need to use this formula is because when it comes to larger sets that say have 50 or 60 or 70 numbers in them, and you need to find the union of those 2 sets, it's kind of hard to keep track of which numbers are in both sets and account for those, right? So let me explain why this formula works, and then you'll understand why you use it on bigger sets. So if we're to find the amount of numbers in just set A, well, there are 3 of them. We have the numbers 1, 2, and 3. So there are 3 numbers here. If we were to find the amount of numbers in set B, well, there are also 3 of them. There's the numbers 3, 4, and 5, right? So this also has 3 numbers. Now, if we were just told that set A and B have 3 numbers each, and it wanted us to find how many numbers were in A union B, well, there are only 5 numbers. So something doesn't add up, right? If we're just to do 3 plus 3, that equals 6. So there are 6 numbers total in the 2 sets, but when we find a union, there are only 5 numbers. And that's why we can't just add how many numbers there are in these 2 sets all alone. That's why we have to subtract something from it, because otherwise our answer will almost indefinitely be too high. And now the reason that we subtract A intersection B is because we're making sure that we don't count any numbers twice. Remember that when we make the union of 2 sets, we don't count any numbers twice. So the number 3 showed up in both sets A and B. But when we find a union, we only put it in once, right? But when we were counting how many numbers there are in set A and B, we counted the numbers 1, 2, and 3 in set A, and then 3, 4, and 5 in set B. And this number 3, we counted it twice. And that's the problem. That's why you can't just add them together, because you're going to end up counting some numbers twice. And specifically, the numbers that you count twice that aren't going to show up twice in the union set are the numbers that they have in common. 3 is the only number that they have in common, and that's the only one we counted twice. And so the reason you subtract A intersection B is because that takes into account all the numbers that they have in common. So for sets A and B, the only numbers that they have in common, as we said, is 3. So this intersection set would just be the number 3, and there would be one number in this, right? So you subtract 1. And there you go. You have 3 plus 3 minus 1. That equals 5 numbers in the union set. Say we had a bigger set where it wasn't just 1, 2, 3 for set A, but say it was 1, 2, 3, 4. Well, there are 4 numbers in set A and 3 numbers in set B. And if we do 4 plus 3, that equals 7, right? But we still only have 5 numbers in our union set. And that's because we have the numbers 4 and 3 in both of these. We counted for these twice if we just add 4 and 3. And so now if we redo our union or our intersection set, then it will have the numbers both 3 and 4. And there are 2 numbers in this intersection set. And so now if we subtract 2, that still gets us to 5 when we change A to having 4 numbers. And that's because we counted for both of these twice when we're just adding these numbers. But then by subtracting 2, we're making sure that we're only counting for each of these once. And that's the whole idea of this equation. And when it comes to larger sets, where you have 50 or 60 numbers in them, it's really hard just to write out all the numbers and be like, oh, well, there are 40 numbers in this union set. You could do that, but it would get messy and it would take a while. Using this and finding just the intersection makes it a lot quicker because there are going to be many less numbers in your intersection set. And then when you subtract those, you'll get the answer for how many numbers there are in your union set a lot quicker. All right, so let me clear all these drawings. And now let me get to this gargantuan equation here. So if you were to find the amount of numbers in A union B union C, well, let's draw some parallels to this equation that we now understand, right? So the first parallel is that you have to find the sum of the amount of numbers in all the sets, right? So the amount of numbers in set A plus the amount of numbers in set B plus the amount of numbers in set C. Now this is where it gets a little bit more complicated. We already figured out that the reason that we can't just add these and be finished is because we're counting some numbers twice. But actually, in A plus B plus C, we're counting some numbers 3 times as well. And I'll get to that in a sec. So for A union B, right, we're subtracting that because say, we'll just go back to our just set A and B example. If we have the numbers, I'll actually just make 3 sets to explain it. So here's set A, 3, 4, 5. This is set B, and then 5, 6, 7, 3. That is set C, right? So if we were just to add all these numbers, here we get 3 numbers in set A, 3 numbers in set B, and 4 numbers in set C, and altogether that equals 11. But there very obviously are not 11 numbers in this total union set, right? So first we need to take into account the numbers that were counted twice when we're finding A and B. So the only numbers that in sets A and B that we have in common are the numbers 3. So when we added 3 numbers in set A and 3 numbers in set B, we counted for this 3 twice. And I realized that there's a 3 in set C. I will get to that. So we accounted for this number 3 twice. So we need to subtract the 1 number in the intersection of set A and B, which is just 3, to make sure we don't account for that 3 twice. Next, we subtract the amount of numbers that we account for twice when we're finding the union of set A and C, right? So when we're finding the amount of numbers in these, we have 1, 2, and 3, and then 5, 6, 7, and 3. Well, we counted for 3 twice, and lo and behold, if we were to find the intersection of set A and C, the only number in it would be 3. So we subtract 1, because there's 1 number in that intersection set. And then we take into account the numbers we counted for twice with just sets B and C. And you can see it's just kind of a bigger extrapolation of this first equation. So we counted for the number 5 and 3 twice in sets B and C. right? So, and then in the intersection set of B and C, we have the numbers 3 and 5, right? Because those are the numbers that it has in common. I'll write this one out. And inside there are two numbers. So we do -2. Now, why do we add the numbers in the intersection set of A union B union C? Well, it's because we account for some numbers 3 times, and we need to account for it once. But when we have 3 sets, and when we account for some numbers 3 times, when we just subtract these intersections here to make sure we're only accounting for numbers once, those numbers that were accounted for 3 times get accounted for 0 times when we finish here. So let me explain with these 3 sets. The only number that is in all 3 of these sets is the number 3, right? And when we're figuring out, okay, there are 3 numbers in set A, 3 in set B, and 4 in set C, we count for the number 3 3 times, because we account for it in set A, account for it in set B, and account for it in set C. Now we make sure that we account for it one less time when we subtract the amount of numbers in A intersection B, right? Because we said, well, we account for set A and B, we're accounting for the number 3 twice. So, and I'll put a counter up here. This is the amount of times we've accounted for the number 3. We've accounted for it 3 times to start. And when we subtract this, we say, well, we've accounted for it twice, so now we need to account for it one less time. So that's 2. Now when we subtract A intersection C, we say, well, when we found the amount of numbers in set A and C, together we accounted for the number 3 twice, right? Because we had it in both sets. So we need to subtract 1 to make sure it's only getting accounted for once in each of those sets. And so that gets us to accounting for it once, which is where we should stop, but we can't, because we have to make sure that we finish accounting for all of the numbers that we have in common in some sets. So in the intersection of set B and C, right, we said, well, the numbers that we accounted for twice are the number 3 and the number 5. Because, oops, I drew an arrow in the wrong place. The number 3 and the number 5. Because those are the two numbers that they have in common. And so, well, we originally started by accounting for 5 twice, but we subtract 1, and we've accounted for 5 once, and everybody's happy. Except for the number 3, because we already have it down to being accounted for once, but when we subtract this number 2 here, that means that we're taking 1 time away from how many we've accounted for the number 3. And now we've accounted for it 0 times. So that might have been a long explanation, but essentially what it means is that when you have a number that's in all 3 sets, when you do this second part of the equation here, when you subtract the amount of numbers in the intersection of each set, you end up accounting for it 0 times. And so that means if we can find the numbers that are in all 3 sets, because those are the ones that are going to end up accounted for 0 times, well, that's A intersection B intersection C, and the only number in that set is the number 3. And so there's one number in that set, and then so if we add 1 here, we make sure we're accounting for the number 3 1 time, and that makes everybody happy. So now if you're to write out the amount of numbers in the union by hand, right? So without using this equation, and just remember that when you get to more difficult questions, you're going to have too many numbers to do this. But just to prove that this works, right? So the union set of A, B, and C will be 1, 2, 3, 4, 5, 6, and 7, right? Because those are all the numbers in all the sets, and making sure you're only accounting for all of them once. If you're to do this equation out, you should get 7 numbers then. So 3 plus 3 plus 4 is 10, minus 1 is 9, minus 1 is 8, minus 2 is 6, and then plus 1 at the end, because look, you're 1 short, because you ended up accounting for 3 0 times. So plus 1 to make sure you're accounting for all the numbers once is going to be 7. And so you have 7 numbers in this union set. All right, so now I have a review question on the inclusion-exclusion principle. If you'd like to try it, I'll give you a few seconds to pause the video, and then I'll explain the answer. All right, so the correct answer to this question was 271. So the question says, how many positive integers less than 1,000 have a 7 in them? For example, 171 and 277 do, and 45 does not. Okay, so how can we use sets to solve this question, right? Because it's asking how many numbers have a 7 in them that are less than 1,000. And just counting this out, like counting the number 7 and then 17 and then 27, that's going to take forever, right? I mean, I guess you could do it that way, but there's a much simpler way to do it, and that's using the inclusion-exclusion principle. And for that, we need to break up the numbers that have a 7 in them into different sets. So let's call these sets set A, set B, and set C. So A, set B, and set C. And you'll see where I'm going with this in 1 second. So the sets that we can break them up into is, since we're talking about at a max 3-digit numbers here, right? Because if it's less than 1,000, the biggest number we're talking about has 3 digits. We can call set A all the numbers that have a digit in the ones place, digit in ones place, or sorry, not a digit, a 7 in the ones place. So 7 in the ones place. We can call set B all the numbers that have a 7 in the hundreds place, or in the tens place, and I think you know where I'm going. Set C is all the numbers that have a 7 in the 100s place. Okay, so for example, set A would be numbers like 277, because it has a 7 in this ones place. It could be 17. It could be just the number 7 on its own, and it could be 997. Like, those are just some examples. Set B has to have a 7 in the tens place, so it could be 170. It could also be 277. It could be 70, and it could be 72, right? Those are just some examples. And set C is all the numbers that have a 7 in the 100s place. And that's simple. It's any number that is in the 700s. So any number from 700 to 799. Oops, to 799. All right. So now we can use the inclusion-exclusion principle, because we have 3 sets, and we're trying to find the amount of numbers in the union of these 3 sets. So all the numbers that these sets include, because that will account for all the numbers that have 7 in them below 1,000. And just as a reminder, the reason we can't just add up the amount of numbers in all 3 of these sets is because we're going to account for some numbers twice. Like the number 277, that's both in set A and set B. So if we just added that, we're accounting for that number twice. And some numbers, like 777, we're accounting for 3 times. And so that's why we need to use our equation. And that's why we need to use our equation instead of writing just everything out, because that's going to take forever. So let's start by finding the amount of numbers in each of these sets. And we'll start with set C, because that one's the easiest. We already said set C is all the numbers from 700 to 799. Well, if we have all the numbers from 700 to 799, that is 100 numbers total. And this might throw you off because you say, well, it ends in 99. Shouldn't it be 99 numbers total? That's assuming you're starting from 701, but we're including the number 700 as well. So that's our 100th number. So there are 100 numbers in set C. So 100 numbers here. All right, now let's say we'll go with set B, right? So every time you have a 100s, or like a two-digit number, there are 10 numbers in the 70s, because there's 70, 71, 72, 73, 74, 75, 76, 77, 78, and 79. And that is 10 numbers total, right? And so we have that in just the 70s, and then we have the 170s, which have 10 numbers total, and the 270s, which have 10 numbers total, and the 370s, and so on. And you can see where I'm going with this. In every single 100, there are 10 numbers that have a 7 in the tens place, right? Because it'll go all the way up to the 970s. And since there are 10 100s below 1,000, then that means you have 100 numbers in set B. And if you see a pattern here, you'll just immediately be able to realize that there are also going to be 100 numbers in set A. But just to prove it, under 100, there are 10 numbers that have a 7 in the ones place. And those numbers are 7, 17, 27, 37, 47, 57, 67, 77, 87, and 97. And just like in set B, in every 100 numbers, there are going to be 10 of them that have a 7 in the ones place. So we'll get all the way up to 900, where we have 907, 917, 927, and so on. That's 100 numbers total as well. So now that we know we have 100 numbers in set A, B, and C total, that means that there are 300 numbers all together in those sets, but we've accounted for some of them twice and accounted for some of them 3 times. And that's where we do the subtraction to figure out which ones we've accounted for twice and which ones we've accounted for 3 times. So first, let's find the intersection set of A and B, right? Because we have to subtract the intersection of all of these sets, or the amount of numbers in it, should I say. All right, so the intersection set of A and B will contain all the numbers that have a 7 in both the tens place and a 7 in the ones place, which means that they end in 77, right? And if they end in 77, there are only 10 numbers that this is possible for. The number 77, then we have 177, 277, 377, and so on. And we'll eventually get to 977, and if you count those all up, that gets you to 10 numbers total that end in 77 below 1000. So 10 numbers here. In the intersection set of, next let's do B and C. Well, let's see. That means that it's going to have a 7 in the tens place and a 7 in the 100s place, right? So that means that it's going to be the number 770 something. Well, there are 10 numbers in the 770s. There's 770, 771, 772, and all the way up to 779. And that's 10 numbers total. So there are also 10 numbers in this set. And if you see the pattern again, you'll know that there will be 10 numbers in A intersection of C, and that was not a good intersection symbol, A intersection C. But if you just want to prove it, it's going to be any number that starts with a 7 and ends with a 7. And there are 10 possible numbers, 0 through 9, that can go in the middle, right? So that means that there are 10 numbers in this set as well. And so from 300, we have to subtract the amount of numbers in all of those sets to get us to 270. And then the final part of the equation that we absolutely must not forget is that when we do this and account for the numbers we've accounted for twice, if a number's been accounted for 3 times, now it's accounted for 0 times. So we have to add back the numbers that are in all 3 sets, right? So that's why we add at the end the amount of numbers in the set of A intersection B intersection C. And the only number in A intersection B intersection C is going to be the number 777, because it has a 7 in the tens place, ones place, and hundreds place, which means that in this intersection set, there is 1 number total. So if we do this 270 that we have plus 1, that equals our 271 numbers as our final answer. All right, and finally, I promise, we're getting to the last part of this section. So we have to learn how to solve sets using least common multiple and possibly modulos. And the reason that I'm talking about this is because there are some questions, like the one I have written below, where just using your basic knowledge of sets, it might be really hard to come up with a way to solve it. So I'm going to teach you how to solve questions that are like this. And those are questions where you have stuff like 3 less than a multiple of 8, or 3 more than a multiple of 2, or something. This question says, suppose A is the set of natural numbers that are 3 more than a multiple of 8. Suppose B is the set of natural numbers that are 1 more than a multiple of 7. And suppose C is the set of natural numbers that are less than 500. How many elements are in the set of A intersection B intersection C? So what it's asking is, how many numbers are in all 3 of these sets? And not like all three of them as in like all of the numbers, but all three of the sets is in the numbers that they have in common, because that's what intersection means, right? And the reason this is difficult is because, well, numbers that are 3 more than a multiple of 8, those are numbers like 11 and 19 and 27 and so on. And like, it's hard to find a pattern for these numbers. Of course, you can say they're 3 more than a multiple of 8, but it's hard to find a pattern and find where other numbers meet that pattern, if that kind of makes sense. So the way that we solve these types of questions is by realizing that the number that, so we need to find a number that set A and set B will have in common. We want to start with the two sets that we have these weird rules for, like 3 more than a multiple of 8 or 1 more than a multiple of 7. And we can get to set C later. Our first job is just to find the lowest possible number that are in both of those sets. So the lowest number that's going to be in the intersection of A and B. And so in this case, I'll tell you what the number is. The number is 43, right? Because a multiple of 7 is 42. And if you add 1, that equals 43. And a multiple of 8 is going to be 40. And so if you add 3 to that, that also equals 43. And so eventually you find one of these numbers and we can move on from there. That's step 1. But how did I get here? I'm going to explain like a better way to try and find this number. It's not going to make it immediate. Like, you can't calculate for it necessarily without using modulos, which are a lot more complicated when we get into it. But I'll just give you a little bit more of a basic explanation. So the way that we do this is realizing that if it's 3 more than a multiple of 8 and 1 more than a multiple of 7, then the multiple of 7 is going to be 2 more than the multiple of 8. And if we look here, that's true, right? Because 42 is 2 more than 40. Because say we have n as our multiple of 8, so n plus 3 is going to be equal to 1 more than our multiple of 7. And say m is our multiple of 7. So n plus 3, so our multiple of 8 plus 3, is going to be equal to our multiple of 7 plus 1, right? These are the numbers we're talking about. And so that means that if you just move over some addition here and you get n plus 2 equals m. So 2 more than our multiple of 8, which is n, is going to be equal to our multiple of 7. So if our multiple of 7 then is 2 more than our multiple of 8, and this is the step you want to get to, now you don't have to worry about the multiple of 8 really, right? You don't need to think, okay, what are my multiples of 8? They're going to be 8 and 16 and 24 and so on. Just think about your multiples of 7. So go through your multiples of 7 on the page and think, well, my multiples of 7 are 7, 14, and then every time you write one down, think, all right, what number is 2 less than it? Well, 2 less than 7 is 5. That's not a multiple of 8. 2 less than 14 is 12. That's not a multiple of 8. And eventually, after you write out enough multiples of 7, and try this for all of them. So 28, 35, right? 2 less than 35 is going to be 33, which isn't a multiple of 8. You'll get to the right number. So you'll get to 42 and say, 2 less than 42 is 40, and aha, that is a multiple of 8. Which means that 40 is your multiple of 8, 42 is your multiple of 7, and the number that's 3 more than the first one and 1 more than the second one is 43. So 43 is going to be your first number that's in both of these sets. Why is that helpful? Because now you can use the least common multiple to find all of the numbers that are going to be in both of those sets. And the way you do that is, least common multiple, which means the smallest multiple that these two numbers have in common. So the smallest number that is divisible by both 8 and 7, in this case, is just going to be 8 times 7. It's going to be 56, right? 56 is the smallest number that's divisible by both 8 and 7. And so that means that every time you add 56 to 43, which is the smallest number that is both 3 more than a multiple of 8 and 1 more than a multiple of 7, you're adding a multiple of both 7 and 8 here, which means that the number that you result with, which in this case is 99, is also going to be 3 more than a multiple of 8, and also going to be 1 more than a multiple of 7. And if you want to check me on that, you can do 99 minus 3 is 96, and that is a multiple of 8. And 99 minus 1 is going to be 98, and that is a multiple of 7. And it's because you're adding a number that's both a multiple of 8 and 7 to your smallest number. That's why you needed the smallest number in the first place. You can use this to find every single other number that are going to be in both set A and B, right? So if we wanted to do this out, we could write it down like 43, and then we have 99 next, and we could keep on adding, right? And we're going to figure out all the numbers that are in A intersection B. And then once you write enough of them out, you just have to count how many of them are less than 500. So, and eventually, if you write enough numbers out, you get to a number like, I actually don't know the number off the top of my head, so I'm going to very quickly calculate it. So 56 times 9 is 504. 56 times 8, 448. Okay, so eventually, if you keep doing this out, you're going to get to the number 491. 491, and I'll put a dot, dot, dot in between. This will be the 9th number that you write down in this list. And so you're going to realize that the next number, when you add 56 again, is going to be above 500. So it cannot be in the intersection with set C. So if this is the 9th number then that you've written down, then there are 9 numbers total in the set A intersection B intersection C. All right, so now I quickly have a review question. If you'd like to try it, I'll give you a few seconds to pause the video, and then I'll explain the answer. So the correct answer to this question was 22. And what you'll notice is that this question is actually in the same format as the last one. And to be honest, pretty much every question that you have to employ these special types of calculations for that you're going to see is going to be in this format. So if you just get familiar with how to do these questions, you're going to be all set. So this question says, suppose A is the set of natural numbers that are 2 more than a multiple of 5. Suppose B is the set of natural numbers that are 1 more than a multiple of 8. And suppose C is the set of natural numbers less than 1,000. How many elements are in the set A intersection B intersection C? All right, quickly one clarification, these parentheses don't matter. If you remember our rules from before, they don't matter. Like, it doesn't matter what order you do the intersection in. So if you want, you can just cross them off because you can do these intersections in whatever order that you want. Now, when we have these types of questions, our step 1 is always defined, and I'll write step 1 here and use the text tool so I can write it out. Our step 1 is always to find the lowest number in the intersection set of A and B. And now I wrote A and B here because that's because that in this question, set A and B are the ones with those weird rules. But really what step 1 is the lowest number in the intersection set of the 2 sets with the weird multiple rules. And in this case, that's set A and B because they have the 2 more than a multiple of 5 and 1 more than a multiple of 8. So we need to find the lowest number in the intersection set of those 2. And the way that we did that last time is by figuring out how much more the multiple of 7 would be than the multiple of 8 that we're adding to. In this case, we need to figure out how much more the multiple of 8 would be than the multiple of 5 or vice versa. And the way we do that is by a little bit of basic algebra, right? If n is our multiple of 5, then n plus 2 will be 2 more than a multiple of 5. And when that's equal to 1 more than a multiple of 8, let's call m our multiple of 8. So m plus 1 is 1 more than a multiple of 8. When these two are equal, then if we just rearrange some addition here, then we get the multiple of 5 plus, not plus 2, plus 1 is going to be equal to the multiple of 8. Or in other words, our multiple of 8 is going to be 1 more than our multiple of 5 because you have to add 1 to our multiple of 5 to get to our multiple of 8. So now what we can do is we can just kind of start ignoring our multiple of 5s and just going through our multiple of 8s. Excuse me, I accidentally erased the wrong thing, so I have to undo a bit. Okay, there we go. Right? Because our multiple of 5 is going to be 1 less than our multiple of 8. Our multiple of 8 is 1 more. So if we start going through our multiples of 8, starting at 8, we can say, okay, what number is 1 less than 8? That's 7. Is 7 a multiple of 5? No, it's not. All right, our next number is 16. What's 1 less than 16? Well, that's 15. And 15 is a multiple of 5, which means we actually just found our n and m, right? And so if 15s are multiple of 5, 16s are multiple of 7, well, one more than our multiple of 8. One more than our multiple of 8 is 17, and 2 more than our multiple of 5 is 17 as well. So 17 is the lowest number that is going to be in both set A and B. Now that we have that, we do our step 2. Step 2, and I'll write it out as well. Find the least common multiple of the numbers in set A and B. And by numbers in set A and B, I mean the numbers where it's like multiple of 5 and multiple of 8. So the least common multiple of 8 and 5 is going to be 8 times 5, which is 40 in this case. 40 is the lowest number that is divisible by both 5 and 8. So that means if we do 17 plus 40, right? So 17 is our number that's in both of these sets. It's 2 more than a multiple of 5 and 1 more than a multiple of 8. Well, we're adding a number that is both a multiple of 5 and 8. So our resulting number, 57, is also going to be 2 more than a multiple of 5 because it's 2 more than 55, and 1 more than a multiple of 8 because it's 1 more than the number 56, and that's divisible by 8. And so we can keep doing that. And we can write out all of these numbers. We can keep adding 40, like next is 97 and so on, and figure out how many numbers there are. And that will work. It's a little bit inefficient though, because we have to go all the way up to 1,000. So the better way to do this, and I did this last time, but I didn't actually explain it because we had a smaller range of numbers. Well, when you have a bigger range of numbers, the best way to do this is to say, well, we're going all the way up to 1,000. So how many times does this number that we keep adding, 40, go into 1,000? And if you do 1,000 divided by 40, you're going to end up with the number 25. 1,000 divided by 40 equals 25, right? So now that you have 25, what you need to do is you need to say, okay, well, our 25th multiple of 40 is actually going to be 1,000, which means our 24th multiple of 40 is going to be 960. So 24th is 960. And so if our 24th multiple is 960, keep in mind that you should be adding 17 to all of these. Then our 25th number inside this list is going to be the number 977. Because we start with 17, and then we get to our first multiple of 40 plus 17, and our second multiple of 40 plus 17, and so on, right? So if we get to our 24th multiple of 40 plus 17, that is our 25th number in this list. And that means that our final answer is 25. All right, just to quickly review what we've learned this lesson. We started with simplifying set theory calculations, where we learned these 3 rules about intersections and unions, and how we can change up the order or change up exactly what we're doing in some set theory calculations. Next, we talked about the inclusion-exclusion principle, which is when you're finding the union of 2 or 3 sets, when you're finding the amount of numbers in that union, you can change it up where you add the amount of numbers in all those sets together, subtract all the numbers in the intersections of 2 of the sets, and then if you have 3 sets total, then add all the numbers in the intersection of all 3 sets. And then we did a review question on this page about that. Then we did a review question about the inclusion-exclusion principle, where we found that 271 numbers less than 1,000 that are positive have a 7 in them. And then finally, we talked about solving sets using the least common multiple and possibly modulos, and found that for this question, there were 9 numbers that are in the intersection set of A, B, and C. And the 2 steps to solving this question is to find the lowest possible number in the intersection set of the ones with the weird multiple rules, and then find the least common multiple of those numbers where you're finding multiples in those sets. And then finally use that to figure out all the numbers in those intersection sets below a certain number. And then we did a review question testing this, and the answer was 25. That's all for today's video. Thank you, and I hope this was helpful. See you next time.